This lesson deals with supplemental problem 314. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems on page 20. Shown here is a circuit that has one PNP transistor, a Zener diode, two resistors, a pot with an adjustable set screw, 12-volt power supply, and a load that can vary. The circuit is called a constant current generator and was published in Nuts and Bolts magazine in volume 24, number 8, and the article was entitled Bipolar Transistor Cookbook, Part 2. This is a collection of very practical bipolar transistor circuits. Could you find this current I if these are the specs of the transistor and the Zener diode? The emitter base turn-on voltage is 0.6, the emitter collector voltage saturated is 0.2, beta F is 100, and the Zener voltage is 5.6. Guess the states of Q1 and D1, and then check your guesses, and if necessary, guess again. In this circuit, there's only one source of power, and that's a 12-volt source. So current's going to come out of here, go back down this way, back to ground, and likewise going to go this way. I would guess that this diode is in the Zener region, and because this is called a constant current generator, this would have to be in the active region. That's the only place where you can get a constant current. So I'm going to guess that this is in the active region. Let's put the model in for the transistor and the Zener diode. Here's my 12-volt power supply, and then I had a Zener of 5.6 volts, a 1.2 k ground, and then I have an emitter here. And between the emitter and the base, there is a turn-on voltage of 0.6, and between the emitter and the collector, there's a current source of beta FIB. I'll put a resistor here R that has the resistance of 470 plus the pot. But when the pot's set to 0, this becomes 470. And then when you go to the other extreme end of the pot, where you get 4.7 K, you can add that to 470 and get 5.17 K. This resistor is going to be varying between these two limits. This will allow us to adjust the current source. And then down here is my load. I'll label the voltage across it V, and then of course the current was defined as I. Let's now analyze the circuit. Current in the emitter is going to be equal to the voltage across this resistor divided by R. We just go around the loop here. I've got a rise in voltage equals the drop of 5.6 and then minus 0.6. That divided by R is my emitter current. In the active region, the collector current is a little smaller than the emitter current by a factor of beta F over beta F plus 1. If I plug in the value of 470 into this equation, I get 10.64 milliamps. If I plug in 5.17 K, I get 967 microamps. And then if I multiply these two by 100 over 101, I get 957 microamps and 10.53 milliamps. And that would be the collector current. Then divide that by beta F of 100, and you get the base current. The base current is greater than or equal to 0, no matter where I set that resistor. And so we are in the active region for that part of the check. To totally be in the active region, I have to have the emitter collector greater than or equal to 0.2. I have a load here, and I don't know what's here. But let's figure out a condition on this load to make sure we're in the active region. This node voltage is 12. I subtract off this voltage, which is 5.6 minus 0.6, or 5, and then minus the drop across here. That would equal the voltage V. If this was 0.2 volts, then I would have 12 minus 5 minus 0.2, and that'd be 6.8. If this was greater than 0.2, then that voltage would be something smaller than 6.8. We'd be subtracting more from this 12. V needs to be less than 6.8 volts to be in the active region. Our assumption would then check, and the collector current is the current I. So we're able to adjust the current I from about 1 milliamp to 10 milliamps. And this is supplemental problem 314.